So, Vanakkam. So, we will continue our lecture on engineering seismology. So, we have been discussing about the seismotectonics of India. We discussed about the northern seismotectonic and the northwestern seismotectonic. Then we have been end up with the eastern seismotectonic in the last class. So, we have been emphasizing the seismotectonics because the seismotectonic details are arrived based on the recorded earthquake in the region. That is one of the very important aspect, where there are several the seismotectonic parameters like VP velocity, VS velocity, the density of the rocks in the region, types of the rocks in the region, and also people make a trench or drill a borehole and confirm a different geological materials associated in the each location, and depth of earthquake, okay, the source mechanism, okay, beach ball, what type of beach ball it is occurring, what type of magnitude it's occurred. So, all those informations are provided in the seismotectonic studies. If you look at the eastern part of seismotectonic, which we are discussing that, so we have seen that the eastern Himalaya, majority of the earthquakes are occurring basically up to 25 kilometer. When you move to the northeastern part, okay, the northeastern part, the earthquakes are occurring from 20 to 50 kilometer depth. So, the Bengal basin, so the earthquakes are occurring in between 25 to 45 kilometer, and also there is a shallow earthquakes between the 5 to 10 kilometer, that also you can see. So, if you go to IBCZ area, okay, so where you can see that the earthquakes are occurring, so almost up to 110 kilometer depth. So, which indicates that when you want to consider hazard analysis at particular location as a source, okay, and then what type of depth you should take. So, that is the information you provided. You can see this is the 3-dimensional figure where the stars are indicating the different earthquakes and then their source mechanism and then the fold thrust belt and the geological formations, okay, all those information you will get from the seismotectonics. So, this is the, you can understand from our discussion that, okay, so the basically the east, okay, and then the west and the north, we have the very complex geological seismotectonical formation which has to be accounted whenever you do any earthquake hazard parameter prediction, okay, for the any development. So, let us come back to the southern part of India, as we discussed well in the eastern and west, and the western particularly we even discussed about the Gujarat, okay, region, okay. So, the western part of India. So, the peninsular India also has a complex geological formation. You can see here, so the Aravalli Craton in the orange color, this is actually Aravalli Craton. So, then there is a Bundelkhand Craton, and then the Chatnapur Craton, and then the Mahanadi Fault, okay, the Basatar Craton, and then Godavari Rift, Dharwar Craton, so Dharwar Trend, okay, Southern Granitul Terrace, and then again this is basically, so the another like Koina region, okay, so there is another. So, this is actually a very complex geological formation. You can also see the minor earthquake recorded in this region, whatever they derived a source mechanism. You can also see the different type of source mechanism. You can see the source mechanisms are not uniform throughout the peninsular India. So, the focal mechanism for the selected earthquakes are shown, like beach balls are shown there. Solid blocks and white dots inside the focal mechanism represent the P and T axis representatively from the shear direction along the west and eastern continental margin can be inferred from that. So, where the shear taking place, okay. So, the Satapura trend, so that is what we have seen, the different geological formation. You can see that wherever there is a joints, okay. So, you can see there is a earthquake in these joints, you can see. So, the geological material basically when it forms with the different geological age, okay, the joints together, and this has a potential to fracture when there is a movement and the other things are taking place. So, this particular data was actually obtained from this publication, which is from the Technophysics on 2016, where I was telling that as and much the data are available, this interpretation and then the understanding of seismotectonics are refined, okay. So, that is what we can see here. So, this is again further a similar kind of this one here they are given like, so the DV is actually Deccan Volcanic Province, this one DV, the green one. So, DC is actually Deccan Craton, okay. So, the BC is actually Buster Craton. So like that, yeah, these are all the actually geological name which indicates the different formation of the geological material there. So this is the geology, complex geology we have seen in the basically our Gujarat region, where you can see the different geological material at movement. This is actually the beach ball for 2001 earthquake. So this kind of studies, okay, one has to go through before doing any analysis, seismic hazard analysis in the region. So this is again the eastern gate belt, so where the Kadapa and other regions are investigated. Here also you can see there are several geological material formation, particularly Ongal and nearby area. So if you see this kind of geological material formation, you can see basically this region, okay, and then this region, or yeah, this region. Okay, 3 regions you can take into account. Then if you look at a seismic activity there, you can see. So wherever there is a geological complex, you will have the more earthquakes. That is what it indicates. So those kind of information will be easily understood from this kind of previous earthquake data, and analyzing the micro earthquake data will help to understand this kind of geological formations and how the crystal evaluation is taking place, what is the crystal velocity there, what is the crystal density there. So this is again the upper and lower mantle anisotropy in India. So this particular article is actually gives the details about the different seismic station, okay, so run on different part of India, and what are the information they collected, okay. So from the entire India, they try to map a different geology complex phenomena, you can see here. Okay, so this is actually the KGF is one of the station. So basically here the so northeast portion they shown here, what are the seismic station they used. Then the GG, basically the GG is actually where is the GG here? So the Godavari Craton. So the Koina where the network are dense, okay, so where they try to map all this information and try to understand, okay, how the seismotectonics are varies in this region using this kind of data. So these stations, okay, some of them are done purposefully to map a seismotectonic. So what they do basically, they deploy a station for a year or 2 years, 3 years, 5 years part of the research project, and then they try to collect a data. That data they analyze. Some of them may be the permanent station, some of them may be the installed station to understand. Based on their observation and wave changes, okay, how the seismic wave changes from this kind of thing, then try to mark a boundary of these plates with respect to spatial variation as well as depth variation. Okay, that is what they try to do that, which is very useful to interpret several geology and seismotectonic behavior of this one. So you can see the simplified model of map of Indian and Tibet, okay, where you can see that the southern granite terrain, okay, basically this one, okay, so this one, and then the western Dharwad Craton, so this one, so then the Kadapa basin, okay, this one, again in that Dharwad Craton there is a complex geological formation, you can see here. So then here this part, okay, so where these are all the places where you can even got some kind of earthquakes, okay, reported on this Jabalpur earthquake, okay, Ongal earthquake, okay, those are all the earthquakes are wherever this kind of complex setting geological formations are available. So these analysis of data, okay, so basically done by the Singh on 2015. So review the present on account of the variation of the crustal upper mantle structure beneath the Indian subcontinent at its environment with emphasis on passive seismic result supplemented by the result using the controlled seismic source. So the people have they recorded the passive seismic waves, okay, which comes from the earth as well as any minor earthquake and anywhere else or major earthquake in all around the world, and that data, and they also used a controlled seismic source like a blasting or some kind of seismic source. So where they try to estimate a receiver function, okay, from the 600 seismic stations over a 10,000 kilometer deep seismic profiles have been exploited to produce a map of average crystal velocity and thickness across this southern part. The crystal thickness varies from 29 to southern tip of India and 88 to the upper of the Himalayan collision zone. So now from this study you can get the crust thickness, okay, the crust thickness varies from 29 to the almost 88 kilometer, Himalayan, the pattern of variation shows the significant deviation from the prediction of global models. So, they here emphasize that the pattern is not consistent with the any of the global similar kind of tectonic pattern. The shear wave velocity splitting results earlier shows that the dominance of absolute plate motion related to the strained highly anisotropic Indian lithosphere mantle, which delay times between the split passes to the 1 second. So, that means the plate movement and the thickness, okay, are very complex when compared to the similar kind of geological formation in the world. So, obviously, because earlier as I told you that it was a island which is called as a Kumarikandam about 70 million years ago, then it was moving towards a Eurasian plate and hitting a Eurasian plate. All this made a very complex geological formation, okay, which happens due to the nature. So, there is nothing we can do, but if you want to predict a hazard reliably, we need to basically understand how these things are varies. Okay, how can we can relatively take a suitable model to understand all this seismic wave propagation in this kind of crust. Okay. The further installation of permanent and temporary station will fulfill these gaps. So, he suggested actually the whatever data he collected and analyzed, even though that is a very extensive study, but he said that there is a need to improve our seismic station, which I also highlighted that as on now the number of station installed in India is insufficient when compared to the seismic activity what we are having, okay, as seismic loss what we are experiencing. So, this is the basically the distribution of the Poisson ratio of the region. You can see how this was varies from the data recorded. So, the average crystal velocity, you can see the Vs velocity, okay, this, okay, from the different network from passive seismic steady substation marked in the inverted triangle. So, where the triangles are the station, okay, from there the recorded data was processed and they try to estimate what is the Vs velocity. You can see that we do not have uniform Vs velocity throughout the India. That means, if somebody want to calculate location of the earthquake, they cannot take a uniform velocity throughout the India. So, some places where you have the 4.2 kilometer, some places where you have the 3.3, some place 3.6, some place 3.9. So, this has to be accounted in the estimation of the earthquake epicenter and depth of earthquake. Okay. So, these article details you can found in these websites where you can get more information about this earthquake. So, this is how the thickness varies at the different part of India from the recorded data they analyze. So, this is the Himalayan and Tibetan plate, you can see the thickness varies, okay. So, from about 40 to 80 kilometer, that is basically a crust thickness, okay. This is the crust thickness, that is what we are discussing. So, then the DH, SC and BU and SGGT, this we have seen like southern granite terrain and all. You can see here this is becoming again shallow. Then NLC and GG, where you can see this was around this range and this one. So, this is actually the dark and the light was given to understand how the values are varies off and then off, more than off kind of things it is there. So, you can see the Poisson ratio, the Poisson ratio of the rock present in the region. You can see here this was Poisson ratio from 0.2 to 0.3. So, this is the 0.25 to 3 and then Poisson ratio of 0.25 and 3 Poisson ratio of 0.25. So, you can see like whenever there is a soil associated the fracturing, more fracturing or Poisson ratios are slightly on the higher side, where the rock the Poisson ratio lower side. So, histogram the crystal parameter and crystal thickness, each box divide the distinct background color to easy comparison of the results. Okay. So, where higher side and lower side comparison of the results is possible, that is why they are given. So, this was kind of studies will help you to understand, okay, if you know the thickness of the crust, then obviously your depth of earthquake and then the velocity of crust are useful. So, this is the histogram again given the Vp and Vs velocity on the region. So, even though we have seen that the Vs has a velocity range of about 60 km per second to the 80 km per second, but you can see the regions like this Himalayan region, the Vs Himalayan Tibet. So, the Vs was actually this range, okay. So, around 6.2 and 6.3. So, where in the other regions where the DS, SC and southern granite terrain, the Vs values you can see here. So, which is slightly larger than this. Here again, so this one the other regions, so which is again the NLC and GG and then the DVP, okay, this region. You can see how the V. Similarly, the Vs, okay, you can see the Vs variation. So, it is not throughout the country the Vs and Vp values are not similar. Okay, that is the message we have got from the analyzing large number of seismic data, passive and active data recorded in the region. So, the crystal thickness map produced using this kind of data and analysis. So, where using the estimated from the receiver functions. So, you can see the thickness of the crust. Okay, so, the pink one is actually very shallow, you can see here. So, then the slightly the blue and then the green, okay. So, then followed by the other color like yellow and darker. So, this also maps on Himalayan region, not only peninsular India. This map was prepared throughout the India, and wherever the white gap is there, actually there is no such study has been done. That is what it indicates, because these people generally they deploy station soon after the some earthquake from funding the from places and try to understand how it varies. These people used totally 834 data points from 621 station have been used to create image. The location of the broadband seismic stations are marked in a inverted triangle, okay, where they used the figure employ points of broadband receiver function, the crystal surface interpolated using the each radius of 100 km. So, the accuracy of this is actually they consider each 100 km, okay, so the segment and then try to interpolate and extrapolate the data of the using that. So, that is why you can see that there are places where there is no data, means there is no station installed there, okay, there is no study has been carried out. So, this is again the heat flow values taken from the global heat flow map published by the International Heat Flow Commission. So, where you can see the heat flow values. So, this heat flow, this is the map of crystal thickness using the published result of the deep seismic sounding by the elsewhere. So, the author basically his results he tried to validate and compare by the other results by looking at all this one and try to give a the map of crystal thickness combining all the available results. You can see now the since the old publication, new publication, he tried to improve where you can see the crystal thickness at many places you can get, but still there are white patches where there is no any seismic activities are taken place. Okay. So, this is the difference in the crystal thickness what he estimated with respect to the so the model, okay, the crust 01. So, data which is published by some, you can see that. So, the negative value, positive value shows thin and thick crust respectively with the respect to the crust 1. Crust 1 is actually where the maybe the global program, okay, where the crystal thickness they might have estimated, how his values are comparable and where it is deviates. Okay. So, you can see that the more or less most of the places the values are variations are very small, okay, not too much. But however, since he has done specific to India, we should give actually basically more importance to his studies. The crust is on a global scale, okay, it is not on the local scale. So, there may be variation, you always expect that, because the crust talks about in the global scale, okay, and how that program, what model they used, and he has done his own receiver function data which will be more authenticated. But since when you talk about in the international community, you have to validate and compare with the global level comparison. So, there are significant variation in the average crust velocity and Poisson ratio across Indian subcontinent. So, with some very clear trend, okay, what we discussed in the slide previously, okay, the regions of Himalaya and Tibet show the significantly lower Vs, okay, like 3.57 km per second. So, if you want to consider estimate a epicenter hypocenter on this region, you should consider this velocity. Then the Indian shield, okay, like the southern India, where 3.5 to 3.75, 3.7 to 3.75 km per second. You can see the difference. So, a second actually causes a kilometer difference. So, so much you can find. If it is 100 km travels, accordingly the time difference will cause a huge amount of error in the estimation of epicenter. So, the Himalayan four strip seismic station and stations in the Indo-Gangetic alluvial plain have the intermediate range of velocity from 3.65 km per second. So, out of 322 seismic station in the Himalaya, Tibet, the 200 seismic station have been velocities less than 3.6 km and 86 even a lower value of 3.5. Okay, this was about the Himalayan and Tibet station, which is run by our Indian this one. Although stations are not uniformly distributed, the results are significant and clear indicate a low velocity crest in the collision zone. Okay, the shear wave velocity lower and lower, okay, will indicate that the regions are more and more complex in nature, and the density and the velocity of the rocks are basically low. Okay, lower shear wave velocity or shear properties are change the S wave propagation drastically. That is what the message you have to understand from this discussion. So, this is basically the lithosphere thickness estimated observed from various receiver function studies. So, you can see here, and then lithosphere thickness estimated from surface wave topography. Can you see? So, this variation, like here the color scales are given based on the topography. Here you can see that the minor level variations are mapped well in this study. Okay. So, on the regional based study mapped well that. Okay. So, this is again the geology map with major geological provinces India with the seismic data what they use. They insert map up top shows a spatial distribution of the broadband seismic station inverted red triangle, okay, whose data and results are used to study and understand the different seismotectonics of the southern part of this one India. Okay. So, what they have studied actually. So, this actually Aldar was carried out this study. It was very recent paper 2017 it published. Use converted wave data to extract a bulk crystal properties in the Indian craton. In order to estimate the bulk crystal properties in diverse craton of the Indian shield, we use teleseismic wave recorded at 82 station being operated by the CSR, the NGRI, okay, National Geographical Research Institute, and the National Center of Seismology. The India further large number of crystal parameters from 2-1 stations published by other workers in India also been complemented our observation. The converted wave technique called P wave receiver function analysis PFR to the large amount of the seismological data, Indian stations and investigated the crust thickness. So, you can see that the waveform, okay, basically they taken a seismic record at different places and try to understand how this wave indicate a different geological parameters in the region, okay, seismotectonic parameters in the region. So, Aldar et al. Have performed bootstrap analysis to show the interpret phase are well above the 2 second, you can see here the phase, okay, Moho depth, okay, you can see the Moho depth, okay, this is the basically the Moho depth, and then the second layer here. So, this is the waveform analysis they do. So, these are all the studies where the seismologist will do. Okay. Seismologist will focus on seismic record and try to interpret this kind of depth, which will give you the depth of earthquake at a particular location. So, the figure 2 basically, so the station wise receiver function image dashed line predict travel time of the simple one layer Moho depth, and then the thin double back lines of the stuck trace plus 2 second bound. So, these are all the Moho depth they interpreted from this kind of data. So, further they used this data to derive a subsurface model at each station subjected to HK stacking analysis to derive a bulk model of the station. You can see the VP/VS ratio and the thickness of that breakage where it happens, crust thickness, Moho depth. Okay, you can see this one. So, this is basically this is the earthquake data what they consider. So, this is the place how it is distributed, okay, the grayscales. So, the estimation of bulk crystal thickness, the bulk VP/VS using HK stacking analysis, the center of the contour are marked white dots denoting the maximum stacking amplitude is expected. The optional bulk crystal parameters are displayed on each subplot. Okay. So, the bulk crystal parameters have been estimated, comprehensive crystal parameters image have been prepared. The result revealed that the crystal structure of Indian shield is variable with the thickness varying from 30 to 50 km. That is what we have also seen, the previous author also told the similar kind of variation of a thin, okay, crust in the southern part, and then the Himalayan region thick. Okay. So, but there is a slight difference. So, about 10 kilometer or 5 kilometer thickness difference is that is okay, that is not a very big amount when you consider the geological studies. The crust thickness below DVP, okay, so was about 30 to 40 kilometer, in average of 38 kilometer. The crust DCE thinner 30 to 40 kilometer with average of 35 kilometer. So the western Dharwad Craton, okay, eastern Dharwad Craton, the crust thickness varies 30 to 48, average of 45. The crust thickness of Aravalli Craton 30 kilometer, whereas the Bundelkhand Craton is 43. All along the IGP Indo-Gangetic Basin varies from 30 to 45 kilometer with average of 37. The average crustal thickness of the Singbom Craton and the Bastar Craton 44 and 42 respectively. The crustal thickness derived from the receiver function are quite consistent with the estimation made by the different workers in the previous studies. The deposit of the 4B, okay, depicts a average VP and VS ratio map of Indian shield derived from our analysis and supplemented by the previous published work. So, they are given what is the bulk crystal thickness and the bulk VP and VS ratio. You can see there is a considerable variation in the geological scale. Okay. Basically, geological scale India is very thin. Okay. It is very small size, okay, when compared to other part, particularly southern India, but you can see the variation within that small, okay, portion like 5-degree portion. You can see how the thickness varies and the bulk VP and VS ratio varies. So, these are all indicates that the geologically and seismotectonically these regions are more and more complex, which has to be accounted when you do any hazard parameter prediction for the future earthquake. So, the figure clearly shows that the Poisson ratio varies from 1.6 to 1.94. Over the shield, most of the data shows VP/VS slightly higher than the normal crust. So, the normal crust is actually 1.73, but it shows a higher trend. So, the bulk Indian crust tend to more intermediate in nature. The Himalayan region and eastern India craton shows large VP/VS value, that is 1.9. So, DVP shows VS/VP value ranging from 1.7 to 1.9, while the Kadapa basin value ranges from 1.7 to 1.88. The eastern and western Dharwad craton bulk VP/VS about 1.7 to 1.84. Now, if we compare Aldar et al. Result with the global average, the bulk crustal parameters fall somewhat near to the worldwide reported 1.7 to 39 kilometer published by the Christine and Moni in 1995, but that is a old data based on the global scale values. So, Aldar found the following conclusion he has given actually. The analysis dominated, okay, by the data from the Dharwad craton reveals that most of the crust formed in the earlier Archean period. So, the Archean period is basically 4 to 2.5 million years ago. Okay. So, that was one of the is finding. Soon after its information, it is gradually altered, making magnetic to intermediate bulk composition. For the present day heat flow values, which was higher the late Archean compared to the earlier, correspond to the regions of thinner crust, implying that the crust formation prevails at a much higher temperature, predominantly although the vertical accretion initially and then slab melting. So, how the plate was formed, okay, how the heat flow was there olden time, and now they try to compare. So, overall his findings say that the Indian, okay, plate stable continent region, okay, has a thin plate when compared to any other intraplate thickness, crust thickness. Because of its thin, it is moving very fast. Because of its moving very fast, it getting to fracture locally highly than compared to any other region. That is why you have the many frequent, okay, so the damaging earthquake in the region starting from Killari, Jabalpur, Bhuj, Koina. These are all the some of the earthquake which happened in the last 50 to 60 years and caused extensive damage than the any other well known earthquake in the India. Okay, so if you the Indian seismicity, if you divide as a two pattern before 1950, after 1950, before 1950 we do not have much record and data except very few earthquakes where the only written data are available. But if you take the instrumented data and known knowledge data in the last 70 years, so the southern India suffered more damage than the north India. Okay, so that was one of the main concern that the scientists start working on the stable continent region results. So, this is basically again the geology and earthquake of peninsular India. You can see a several earthquake which is plotted, okay, the geology Peninsular India, okay, derived from the geological map of GSI 2000, location of historical earthquake circles. The color diameter of circle indicate depth and magnitude respectively. So basically the geological terrain is given here and the size indicate here your size of earthquake, the color indicate here this. So you can see that the most of the earthquake, okay, except this one. So most of the earthquake in southern India are the shallow in nature. So this basically, okay, this kind of shallow earthquake may cause a devastating, okay, so the damage than the a deeper earthquake. You can see if you go slightly higher part, you can see here the earthquakes are around like 40 kilometer depth. Okay, so here these are all shallow earthquakes are the so the major event occurred during the 50 years indicated by the red stars. Okay, so this is the like the Koina earthquake, Latur earthquake, Jabalpur earthquake, Bhuj earthquake. You can see how these are. So these data are available and published in the 2016 by the CMAX scientist, group of CMAX scientists. If you get more information, you can visit that page. So these people, how they use a catalog for compiling this, actually they used a catalog from IS reviewed bulletin since 1960 and the PDE catalog 1973 USGS National Earthquake Information Center, IMD Indian Meteorological Department from 1898, catalog prepared by the NDMA from various resources, their report, okay, from 2474 to 2008. Okay, so NDMA report, National Oceanic and Atmospheric Administration NOAA catalog, and then the event listed by the Oldham and the Tendon Chowdhury and then the Chohu, okay, all those people, Ramalingeshwar Rao, Sedibadi Rao. So all those people data are these people considered to prepare a previous map. So this data, if you study this data how individually varies, so you can see this plot. So basically the plot A, okay, this one, so indicates the Indian catalog compiled in this study from various resources. Okay, so where the data descriptions are given here. So the data B is this plot is basically similar to A, but excluding the introduced by the Ramalingeshwara Rao and Sedibadi Rao. Okay, so where that book yesterday I was telling, no, so that data was excluded. Then the C is PDA catalog since 90. So this is the catalog from that, and then the D, okay, this one the IS catalog since 1960. So the shuttle radar tomography mission also they used USGS kind of catalog. You can see the distribution. Okay, so this is the compiled all the data. So now you can understand that the data, okay, where from we are obtaining, how the data are reliable, also gives the indicate the how your interpretations are accurate enough to get the some analysis. So overall what we discussed so far, I am going to summarize in the next 3 slides. We have been talking about the seismotectonic of Indian region. So we have talked about the India as actually a major two group you can divide, okay, the North India and South India. North India has actually the complex geological formation on northern side where there is a subduction and a continent, okay, so the active crust region in that, and the western part and eastern part as a transformed boundary where the thrust faults are forming due to the transformation action between the Eurasian and the Indian plate. So if you come the eastern part little down Sumatra region, you have the complete subduction activity there which is below the sea. Okay, so then if you come back to south, so south there is no any kind of major plate boundary exists, but there was a formation, okay, the land formation has a different geological region, okay, so different craton, different like the magma, so emission and formation, melting. So all those created a different geological units, okay, that geological unit, the joints and associated the fracture in that region causes a earthquake. So those earthquakes we need to broadly account in the hazard analysis. As I told you that this is the subduction zone, active tectonic, subduction in slab, okay, subduction interslab and a stable continent. So, this earthquake occurring here, most of them are localized activity because of the geological formation and the activity, seismic activity or seismic force created by the movement of the plate of Indian plate and while hitting the Eurasian plate, whatever is happens, folding and fracturing. So, that causes here this one. So, this is how you can make this is the model which was actually considered for the global earthquake model, Northern Thimbajam what they use now. This is the model they consider. They made it everything as a 3 major category, and then they try to account the respective ground motion models and equations for the estimation of hazard, which we will be discussing in the next class. This is the source and beach ball what they use. You can see based on the different earthquake, they consider this as a model to estimate a global seismic hazard. So, which we need to be, they have taken on the macro scale, okay. So, which will be in detail, we will be discussing on the earthquake hazard analysis, which will be from the next class onwards. So, the seismotectonic, the understanding of geology is very important to decide your earthquake hazard input parameters. Okay. So, what are the input parameters? What magnitude you should consider, what focal depth you should consider, what the source mechanism, beach ball you should consider for the simulation kind of things, what is the crust thickness you should consider, what is the VP velocity, VS velocity you should consider to interpret a seismic data, okay, to locate a earthquake. Okay. So, those are all the informations are essential which has to be derived from the region specific data. At least now we have the subsequent studies and considerable amount of data is there. When I was doing seismic hazard analysis of Bangalore in 2004, no such steady data was available. Okay. So, I made a lot of assumption actually, but now these data are being available. This also considered in the recent seismic hazard analysis of South India by my student Ketan Bajaj, and also the site specific hazard analysis and rupture based analysis by the Silas Abraham, the another PhD student who is working on the dam seismic hazard analysis and all, where we try to account these information whatever I studied, no, we try to account in the hazard analysis, try to estimate reliable hazard parameters for the design and other activity. So, that we are going to discuss in the next class. So, thank you very much for watching this video. I will meet you in the next class.